Hi there. So hope you've sort of found some of the previous videos discussing the concepts of complex variables and the geometry of the basic algebraic operations somewhat useful. So now maybe we should start talking about what are the functions of complex variables, and this will really open up an array of topics and applications. So let's get started with that. So before we start talking about functions of complex variables, let's just review the basic idea behind what a function or a mapping is between, let's say, two arbitrary set of objects. So let's say we're given two arbitrary sets, a set X, which contains elements set that we denote by small x, and then we have some other set Y with object small y. Then a mapping from set X to set Y is a rule or a correspondence, typically denoted by f going from X to Y. So it's a rule or a correspondence that takes an element small x belonging to capital X and maps it to one element small y in capital Y, right? So it's a rule. So let's say a mapping is a rule that maps or that assigns to an element small x, to an element small x belonging to the set X, unique, and this y is called, under the mapping, is called the image of X. Image of X under the mapping F. So a mapping is a rule that assigns to an element small x belonging to capital X a unique image. We can just say an image or a unique image y belonging to the set Y, right? So just to sort of restate this, to each small x there is only one small y belonging to capital Y. Now this sort of definition holds true for any set X and any set Y containing an arbitrary objects. We haven't specified any particular we haven't specified the nature of objects that belongs to these sets. So the idea behind mapping is that it's sort of you can think of it as a way of communicating between two arbitrary sets. So we have one set X, we have one set Y. How do we communicate between them? And in order to communicate between sets, we introduce the idea of a mapping. Okay. Now when we specifically focus on objects of the form real or complex variables or numbers, or in general any kind of numbers, then people typically use the idea that this kind of a rule is called a function. So for our purposes, we wouldn't distinguish between what a function is and a mapping is, and what we'll say is a function or a mapping, we'll just use them we wouldn't distinguish between them, and we'll say that a mapping that takes us from the set of, let's say, real or complex variables to another set of real or complex variables, we can just call such a mapping a function. So for us, we'll just use this definition for both a mapping and a function, and we can call this also a function. And that's why there is sort of a generically, people use the symbol small f to denote a mapping, because most of the time we don't really distinguish between a mapping and a function. And then we can say that, or in cases where we have sort of we have gotten rid of any sort of differences between these definitions, we can also say a mapping. We can also write a mapping from set X to set Y in the form Y is f of X. So we'll say that small y is the image of small x under the mapping F, and F is called a function. So that's the basic definition of what a function of a mapping is. Okay, so now let's focus on the case when we have, let's say, a function y equals fx, where x comma y belong to real variables. So let's focus on this specific case, which is somewhat familiar, that we have a mapping or a function from set x, which is a set of real numbers, to a set y, which is also a set of real numbers. Now, one of the ways to depict such a mapping or a function is to make a plot. So how do we make a plot from set x to set y? So one of the things is, if we go back to the way we were drawing sets, we had a set x, we had a set y, and then we draw an arrow from here to here. So the way to draw this kind of a image for the set of real numbers could be, we draw the real axis x, and then we can draw an imaginary axis, we draw the real axis y, right? And then we can say that, okay, we have some element small x belonging to x, and we draw an arrow to the element. So let's denote elements in y with circles and a dot, and elements in x with a cross. So we can draw an arrow from a cross to a circle with a dot, and we say that under the mapping f, this particular element maps to this particular element in the set y. So this could be one way we can draw these kinds of maps. So for instance, if you have another element small x, its image might be somewhere here. So we can draw an arrow like this. We might have some element here whose image is here, and then we can draw an arrow like this. And we can depict sort of this function using this kind of a plot. But we know that a more useful way to visualize these kind of plots is to instead make a diagram of this form. So instead of drawing the y-axis horizontally, we can draw it vertically, and the x-axis, and we can keep the x-axis horizontal. And in that case, the mapping might look like a function of this form, or a graph of this form. And in this case, we know that this element maps to this element x belongs to this element y, this element belongs to this element belongs to this element, and so on. So this is a somewhat more useful way of making plots from one real variable to another real variable under a mapping f. Okay, now we can generalize these ideas. So first of all, we can generalize the definition of a mapping that takes us from one real variable to another real variable, and generalize this to complex variables, and say that we might have a map that takes us from the set of complex variables z to another set of complex variables, which is generically denoted by the symbol w in this case, and f is again a mapping that takes us from z to w. So in this case, we have the set z, and we have the set w, and we have some element here that maps to some element in w, small z and small w. Okay, now if we try and extend the idea that it's often useful to make a plot for what the mapping looks like, then we see that we have a bit of a sort of dilemma, because a complex variable z is of the form x plus iy. So that's z. Now, since the mapping is taking us from one complex variable to another complex variable w is also a complex number or a complex variable, and typically w is denoted by u plus iv. So now we have four variables x, y, u, and v, and in this case, u is actually a function of x and y, and likewise v is a function of x and y. So a natural question that arises is, how do we make a plot of four variables? And it's not at all obvious how we can depict all the information that this mapping conveys in just one diagram. And therefore we have to make some choices. So again, just to remind ourselves, there are four variables we have to deal with, and that is the reason why we have to make certain choices that are not at all obvious from an understanding of how we map a single real variable to another single real variable. So some of the choices that are often made are, so one of the choices that could be made is make a 3D plot. Okay, since u is a function of x and y, and v is also a function of x and y, if we draw the xy axis, or rather we draw the real and imaginary axis and now label them x and y, and then we can make a plot of u, which will be a 3D plot, and another plot for v, which will again be a 3D plot. So we can make two three-dimensional plots depicting the real and imaginary parts of the variable w. So w is again a function of z, which is of the form u plus iv. So u is the real part of w under the mapping f, and v is the imaginary part. And so we'll have to make two three-dimensional plots in order to convey all the information that this mapping has to convey. So one plot for U, one plot for W, one plot for V. Another possibility is that since W is a complex variable, we can make a plot for modulus of W and argument of W. And again, this will be a function of x and y. So this is a function of x and y, and this is also a function of x and y. So we'll have to make, again, we'll have to make two three-dimensional plots. So that's one of the possibilities that we can make use of. Another possibility is that we can, so that's number 2, is we make our real and imaginary axis, label them x and y, and now we know that we can now make use of the fact that a complex variable can be thought of as a vector with a magnitude and a direction. And what we can do is we can go to the point x and y where we want to make a plot for W, and at that point make an arrow which corresponds to, which depicts both the magnitude and direction of W, right? So at this particular point, W might, the magnitude of W will be, so the magnitude is square root of U square plus V square. That's the magnitude of W. Magnitude of W is this, and similarly we can draw the argument of W, which is tangent inverse of V divided by U. So at this particular plot, at this particular point, we can make an arrow with this magnitude and making an angle, which is argument of W. And we can repeat this process at every point in the xy plane, and we might have some kind of a curve, some kind of a diagram consisting of many vectors. So this is like drawing a vector plot for W. So this is sometimes also called a vector plot. W. So this is another possibility that we can make use of. A third possibility, which is quite often used as a starting point and very often used, is to make two copies of the complex plane. We make a copy for the z plane and label the axis as x and y. So this is a complex plane, this is the real axis, and this is the imaginary axis corresponding to z. And we make another copy of the complex plane and label the real axis as u and imaginary axis as v, and this is called the w plane. So this is called the z plane and this is called the w plane. And the typical idea behind making this copy is that under such mappings, many of the times what we're interested is how does a particular curve in the z plane map under f onto some other curve in the w plane. So it might look like this in the w plane. And so the idea is that we are given some kind of a curve in the z plane. We calculate u and v under this mapping for points on this curve, and then make a curve in the w plane with the appropriate values for u and v. And this is kind of a diagram making two copies of the z and w plane is very often used in the theory of complex functions. And so in the next part of the video, let's make use of this particular possibility and see how some simple functions map from the z plane to the w plane, how some curves rather map under some simple functions from the z plane to the w plane, which will make some of these ideas clearer. And the other possibilities like making 3D plots and vector plots are also often used, and we'll try and make use of them in some later videos. So hope to see you in the next part of the video. Thanks.